Good morning. Good morning. Yesterday we talked about section 1. Supposedly you should be able to finish section 1 homework. I assigned homework on web work. Do you have any questions as you practice question on web work? Any issues, any difficulties? So far there's no problem with it. Yes.
Yeah, I'm having a little trouble like figuring out what like how to find the equation for the different limits.
Let's see. The question that we had so far, the function is given.
Yeah, some of them are just like from the graph though.
Okay. Yeah, we can try one. The first two we did it together. That one.
Yeah, it's no. It's mostly like the last one. Like problem 7.
Oh, okay.
Sorry, not being very clear. Yes.
All right. This one has 2 functions. So we have the G is the red one. So using the graph to represent function. So we're really looking at the limit when the 2 functions added together. Yeah. So let's see the first question. We're trying to find out the value of fx plus g of x. So we don't have the formula, but the graph can indicate what will be the value. For example, if x approaches 1, so for both of these graphs, since the limit, are you able to see it if you are in the back? So which one? The naked one. So x is approaching 1. So then this on the x-axis you'll find a 1, and on this x-axis you also find 1, and then you're going to try to look at 1 over the graph at 1. You can see the left side and right side are also push that point. So this first function, f of x, has a value 1, right?
Yeah.
So for f, we are approaching 1. And then the second function, again, you'll find the 1 on the x-axis and relate to the graph. At 1 from the left side is 1, but from the right side is
0.
Is 0. So then for g of x, there's no consistent answer to the limit. So basically, g of x has no limit. And then therefore, for the entire question, we do not have a limit.
So how exactly would you go answer that? So how exactly would you apply an answer to number 1 though?
I think we put E and E. I guess we can click on the notation. See, limits that don't exist, we will enter E and E, which represent does not exist.
Oh, okay.
So for the first question, we'll enter D and E because of the g of x. The second question has x approach 2. So for both of these graphs, we're going to look at x approaching 2. So you on the x-axis you find 2. It looks like left side and right side both approaching 0. For g of x, this one, we find 2. You can see they have
1.
A 1. So basically 0 plus 1, the answer is 1.
I see it now.
Okay. So that's really when we have no definition of the function, the graph can suffice as a definition for. Like this will replace the formula.
Okay, so yeah, I think I was probably just like overcomplicating it.
Sometimes they just take some examples. If we submit them, you can see at least one of them are not right, since I only did 2. Oh. It says here, in order to get credit, you have to have all answers correct, and that's what's making this slightly harder. Let's finish the rest for 0. That was 0. That was 0.5. but it's multiplication, so 0 times anything is 0. This one at 0, f of x approaching 0, so 0 divided by anything is 0, 0. The last one at -1, -1, so 3 plus -1, which is square root of 2. That would be 5.
There we go.
So because it says we can't get credit for it unless all of them are right, so we try all 5.
All right.
Any other questions? All right, I hope you start right over with section 1. I have students that delayed it for a week or so, so sometimes it does take a lot of time when we are behind. So try to, as long as you understand it, try to finish the part that you understand. Even if you didn't finish all of them, you finish most of them that you actually know what to do, and enter your answer. Try it to test your own understanding. And it's kind of comforting to say that you get certain question to understand it, you already know what to do. So instead of leaving it behind, even you feel like I understand it, even though I didn't answer the answer, but when you try yourself, you truly know whether you understand it or not. Sometimes we felt like we understand it, but if you don't do the calculation, there's a little bit delay between the actual learning and the understanding. All right, let me record today's attendance. Was a question that we were doing yesterday. It's similar to the question that we had about the flying objects, one of the very common problem in physics. In this question, we were given the position function. So the formula is given. We want to find out the average velocity from 1 to 1.01. So this is very similar to the question that we had on homework, the second example on the homework assignment. The difference is unit. This question uses meters for the distance. It uses meter per second for the velocity. That's what's different. In the example that we had yesterday in the text, it was 16 over here because that one used feet per second. I think that was the difference. So using different units, you will end up having different coefficient. That's why its coefficient is different. All right, let's see. You guys do the calculation. I have the scanner set up. Thank you. Oh, yeah. I can find you in the class list. I was handing it out yesterday at the beginning of the class. Do you see your name? It's alphabet order in the last name. Okay, yeah. That's hard. Have you seen your?
No, I'm in the art.
Oh,
This is the choice. Wait, I clean.
You finish calculating it, and I'm ready to scan your answer. Now, you want to repeat your calculations to double check? It should be it's a slope actually. Average velocity is kind of like a slope of the secant line on the function. This is a throwing object, so the motion of the object follows the trajectory that's described by this function. So you want to find out what happened at t. T is our independent variable. T equal 1 and t equal 1.01. So you would go ahead and calculate what is the y value at 1. So that's 58 minus 0.867, 57.17. Yes. So that one I can just subtract the since t equal 1. The second one you have to look at the detail. Like 1.01, what would be the height equal to? And then you would subtract and then divide to find the slope. So this average velocity is slope of the position function. So equal to, finish that calculation, number minus the 57.17 divided by 1.01 minus 1. That is the calculation. There's a missing number there. I didn't finish it because I don't have the tools to get a number calculated. You can also plug in the entire formula. If you feel like less comfortable with the idea, feel free to talk to your neighbor and share your answer with each other. All right, the more we talk to each other, the more we confirm, hey, everybody else is doing this way, that is probably the right calculation. Try to confirm with everyone around you that you're on the right path. Yeah, the card is right. It has 4 sides. When your answer is ABCD is multiple choice, you can say your card this way so you can scan it. Then in the system, it will record your solution. Right. If your answer is already recorded, your name will be highlighted. And now you know that the answer is already recorded in the system. No surprise to your calculations. Board. So I do the calculation. Right, so the numerator should be the y value subtracted, and then the y value has to be calculated based on the x value, and then the yeah, we got it. So we calculate the y value, so you go 58 times 1.01. So you're gonna plug in the x value, 0.83 times 1.01 squared. That's the y value for 1.01. You have to minus the y value for 1. If this is a 1, you will minus what we subtract is 58 times 1 minus 0.83 times 1 squared, which is that. Then that is the subtraction in the numerator. First y value, second y value, subtract them, and that does what we intend to do over here. And now I did calculation mentally, hopefully it was not wrong. Then we divide it. We divide. That's pretty much what you're going to enter into a calculator. So if you're using a calculator to do the calculation, that's everything we should enter. And then the denominator should be the subtraction of the x value. Show a slope in the numerator, you calculate subtraction of the y value. In the denominator, you calculate subtraction of the x value. Okay. Any questions? So that's how we enter. So I'm supposed to enter this into a calculator to make it easy for you to see. Right, so the answer is that. Any questions?
I'm not done with mine yet.
Okay, that's the calculation. So if you enter the calculation, you can, this is the overall structure. Numerator is subtraction of the two y value. Denominator is subtraction of the two x value. Okay. Yeah. So this is the name of the class. If your answer is submitted, it will be your name will be highlighted and know that they got. So I'm trying to get everybody's answer in the system.
For the, I still haven't got the divided chart here yet. Sorry.
There we go.
I couldn't see very well.
Edgar? Not in class today? So maybe we're missing one person today. I can bring it here.
Yeah.
You got your answer?
All right, I just need to see, like, I just need to see the,
The answer.
yeah.
Okay. Okay. Yeah, so as you can see, I did show it, the numbers already there, 56.33. So the answer should be, so you're on the same page. Did you have the wrong one earlier? Okay, and that is possible that when you are putting down your card on the table, the cold part, you try to make it face down because you guys are really close to me. So when you're putting your card down, the scanner accidentally pick up the image. It may change your answers. So that's why I felt like you had it right before, but on the system, it was wrong because it picked up a second answer as we go through the. So can I see your answer again? All right. Anybody else? Okay. Right. So can I see yours? Let's see. Let's do one. Christine. Christine, is that you? Let me see your answer again. It was supposed to be C, but then I see a few wrong answers. I feel like maybe it's because the scanner picked up the wrong image. All right. Just when your answer's already recorded, you know your answer's already in there. You should have your card face down. This face down. So as I was scanning, I won't be able to. I will not. accidentally pick up the wrong image in the system. And then if you already answered C, but then your card, the scanner might think there's a second answer of B if it's accidental scan. All right, this is a question that kind of echoes what we were talking about yesterday. It is a calculation of a slope, but tangent line has a slope, secant line also have a slope. If the line cross the curve at two different points, this is called a secant line. Secant line. All right, but if the line crosses only at one point and tangent to the curve, then this is called a tangent line. Slope of the tangent line is actually the derivative. Slope to the secant line is not. But the reason that we calculate slope of secant line is that it is useful to calculate secant line as a substitute of the calculation of the tangent line. And also we can look at the tendency. As we make the 1.01 smaller, we make it like t equal 1.001 or 1.001, we're getting closer and closer to 1. Then the secant line slope will get closer and closer to the tangent line slope. So calculation of something close to the true solution often give you an idea what was the true solution supposed to be. So if that is kind of the mathematical thinking. When doing something was difficult or impossible at times, and try to solve something close, but not entirely the true question, and will help when you try to find the right solution. All right, today we're gonna try to start section 2. Hopefully that will be section 1. If you have any leftover questions from 1.1, please let me know. All right, so today we're gonna move on to a second section, not just 1. Let's talk about the definition. All right, 1.1 is the informal definition of derivative. 1.2 is actually the formal definition. In the past, I tried to avoid it, but it's something that you will have to talk about in your if you are in math major or science major, sooner or later you're gonna hear about it and think about it and try to figure it out. So we'll try, I guess, instead of putting it off, it's better just to go ahead and talk about it. We try not to spend too much time on it because mathematical proof is not the top priority in this class, but understanding it is. So this is called epsilon delta definition. The word epsilon is a Greek letter. We commonly use it as a quantity. It's impossible to record what's on the screen. So I guess I'll just try to write on the computer here to refer back to it. All right, so epsilon and delta, they are Greek letter. All right, so that is a pronunciation for this. It pronounces as epsilon, and then the other name, delta, is like a little triangle with a little hook on the top. And that's the lowercase delta in Greek alphabet. If you wonder, there's actually a capital letter, epsilon, delta, but these are the two that we use most commonly. So why are we using Greek alphabet in mathematics? I think part of the reason is we often run out of English letter. Another reason is that we try to differentiate it. The physical meaning of a quantity, we often use an English letter, and then the non-physical one, like the hypothetical quantity for comparison or for reference for intermediate variable, we use Greek letter more often. So anyway, these two letters are representing a quantified way to describe how close can it be. When you are trying to consider a limit, we see the limit equation is limit of too small. A little bit better. Right. So just type out the whole thing. Limit of f(x), and x is approaching a certain value c is L, right? That's our notation. That's the abstract notation. So x is approaching an x value c. So c is on the horizontal axis. It's supposed to be on the x. It's supposed to be one of the x values. And now L is where the y value is supposed to approach to. So L is a number on the y-axis. So the C and L actually represent a point on the xy plane. So here you go, the C. And here you have, supposedly, you have the L. And if the function behaves kind of like this, right? And that's where you see the possibly a limit point. All right, so we're saying that when you try to define it informally in section 1, we have a couple different ways. We say as x approach c, or we also say as x gets closer and closer to c, the y is getting closer and closer to L. We can say the y is approaching the value L. So you can see it in a couple of different ways, whichever that makes more sense. But they are informal in a way. You see x is getting closer to c. How close is it? You see y is approaching L. How do you know it's approaching L? So now being able to quantify the phenomenon of a limit approaching limit, the limit evaluation, that is the same with informal definition. In mathematics, we try to get everything solid. We want to get it to be able to put a number to it. So these two numbers, the delta is to describe distance between x and c. So a lot of times you see how close is x and c. Now x can be here or here. So when x is close to c, then distance between x and c will be really small. So it actually be here, here. So how do we quantify distance between two values with subtraction? So we would say x minus c. It is almost as small as delta. So delta is a really small number. And that is a small number that quantify the difference of these two. So we say it's so close, x is so close to L, that the distance between x and c is smaller than delta. So that is one that the delta is what we're using to quantify how far is x to c. Now, similarly, we are using epsilon to quantify. We see f of x is getting closer to L. So how close between these two? So close that f of x minus L, it is less than the epsilon. So the differences between these two numbers is smaller than epsilon. Epsilon typically we choose a small number, so epsilon could be 0.1. So then f of x is close to L by 0.1 distance. That is how we know these two are close enough. So we'll say when you see the limit of fx equal to L, then x approaches c, which is saying I know that f of x is getting closer to L by you can make it as close as you want to. So if you want f of x and L to be closer than 0.1, and all you have to do is find the appropriate delta. So x and c have to be closer than a certain number. So this two will be closer than that number. And that's really the idea behind the epsilon delta definition. Hope that kind of makes sense. So logically, we try to see, you see these two are close. How do I know that? Well, we can make it as close as it should be by making x to c as close as the delta. This is a theoretical reason for definition. So here, a little bit of background from the book. This is taken from the textbook. A couple of different ways to define the limit, an informal way to define limit. Now, the formal formalization here, what I was talking about earlier was all that, and you will describe the distance between x and c to say that x is within delta unit of c, and then the corresponding value of y will be within epsilon unit of L. So that is the usage of the two Greek letter alpha and epsilon and delta. So try to formalizing it, and here are the actual definition. There are a lot of key terminology, and they start becoming part of the definition. So those words are going to be always the word we're using. So notation-wise, limit of fx equal to L when x approaches c. So that is how I'm reading the notation here. So how do we know? How do we prove this? You want to prove this limit calculation using the formal definition. This is how you can prove it. You have to prove for any given epsilon, you can find a delta between these two, such that for all the x value that is close to c by being less than delta, you will find f of x and L have the distance less than epsilon. So making x close to c using the delta allows us to make f of x close to L by the distance being less than epsilon. So that is the definition. So this has become something I have to recite, I have to memorize, because every time I want to prove something using the formal definition, I have to write everything down as it is. Because of the memorization task, and when I was in college, we have some short notation for it, so it won't be so many words. So see, given any, it says any, so I have this notation. I mean, if you think about it, I learned logic, mathematical logic. It's a course, it's one of the subjects. This pronounced any, so this is epsilon A. For any epsilon, positive epsilon, we can find, since there exists. So meaning that you have the task, if you want to prove this limit, you're going to find out that delta, what that delta is supposed to be. So then whenever x and c subtract less than delta, you will find f of x minus L has a distance less than epsilon. So try to work it out to make the notation shorter. So for any epsilon, you can, this is the left and right, switch the left and right E exists. There exists a delta, which is also supposed to be positive since we are quantifying the distance, such that for all x, that's x, you can also do for all x such that x minus c is less than delta, we would find f of x minus L less than epsilon. So these two quantify the distance, these two are determination relation to. Any questions? I hope that kind of shorten things around. I mean, being able to make things concise so it's easy to see the pattern is one of the things we do in mathematics. You may have something that sounds a whole lot when you're trying to see it with English, but you can concise to a few words, a few sentences, or a few notation, and then even further, even the English can be shortened into some notation and symbol, so it becomes even less in terms of memorization and relation. Any questions? As long as you're not in the class for proofs, for now, there's no danger of have to memorize them, but understanding them definitely helps. And then essentially, the limit, the concept of limit is relation between x and y. So as you're pushing x close to a certain value, if the y also approaches a certain value, then the limit exists. As long as you understand that relation, you'll be okay. Basically, x affects y. If x affects the y in the way that they're calling the y value approach certain number, then the limit exists. If the x change does not cause the y to approach anything, and we would not have a limit. There are three scenarios that we talked about yesterday. All right, so let's look at how it works. Nobody had a set right over here. Okay. Look at example on how to use this definition. Okay, so here we have an example. You can graphically illustrate that definition, or you can numerically use that definition. So, like we said earlier, you can calculate all you want with numerical calculation to find the limit, but they're not suffice as a proof. So here you say limit of root of x when x approaches 4 is 2. And I can do the calculation. I can plug in 4, and root of 4 is 2. So that doesn't mean this is a proof. To actually prove, we have to show that tendency, showing that if x is getting closer and closer to 4, and the root of x is getting closer and closer to 2. That's the idea of limit. So what do? We're trying to. So let's look at the graph here. First, we're going to graph the function root of x. So this is y equal to root of x. So the blue curve is graphs. So we're saying we want to try to get the root of x. Try to get root of x closer to 2. So on the y-axis, we find 2, right? And so let's make an example. For example, we know that if x is closer to 4, the y will be closer to 2. So how do we still show that? So we can try to make x y closer to 2 by 0.5. So we're saying I can make y closer to by 0.5 distance. So how do I do that? So you go 0.5 below and 0.5 above from the 2 on the y-axis, and that allows you to draw a band. Why do I draw the band? I guess it's the meaning of the absolute notation. F of x minus L less than epsilon means that f of x and L is very close. So if you remove the x value, and that causes f of x minus L to be less than epsilon and bigger than negative epsilon, and then we can move the L to outside the middle term, and that's causing us. Let me explain the inequality, and that's also the reason for the band. All right, so over here is f of x minus L is less than epsilon. So mathematically, if you get x value of a less than epsilon, that means a is less than epsilon and a is bigger than negative epsilon. So on the number line, you go, this is the a. So if a has epsilon value within epsilon, that means this is a is between the epsilon and negative epsilon. So then the epsilon value would be the 0 here, and this is a. So this is how we know the absolute value of a would be within of the negative epsilon. Something that we have for, right? With it, we're okay with removing the absolute value. So this is a common way to remove absolute value notation and remove it by a relation. So we do the same here. We'll have f of x minus L. It's kind of like the a is less than epsilon or bigger than negative epsilon. Then we hope to get f of x by some f(x) to represent the y value. So f of x will be less than L plus epsilon and bigger than L minus epsilon. So we add L, add L, add L to all three, and that's what's causing this. So basically, this notation f of x minus L x value less than epsilon is the same thing as saying f of x is less than L plus epsilon, bigger than L minus epsilon. Same thing happened to the x value relation. X minus delta is less than minus c is less than delta. It means x is right around, basically it's indicating x and c is very close. So we would say x is less than c plus delta, but bigger than c minus delta. So c minus delta, c plus delta provided the left boundary and right boundary for x. On the other hand, for f of x is supposed to be really close to L, so then L plus epsilon and L minus epsilon would be the left boundary and right boundary for the y value of x. All right, with that idea, I'm trying to explain where do I get the band on the picture. So we're choosing epsilon being 0.5. So we're choosing this number is 0.5, and this number is the 2. 2 is our L in our case. So limit of the function equal to L is a hypothetical abstract definition for the limit, and we now have an actual function f of x, an actual L, and actual c. So c is the 4, L is a 2, f of x is a root of x. So with all that being replaced, we understand that the f of x, or y is between 2 plus 0.5 and 2 minus 0.5. That's why we have this 2 boundary, 2 minus 0.5, 2 plus 0.5, which provided the lower bound and upper bound for the y value. And that gives us the band, the horizontal band that crosses the curve of root function at these 2 red points on the graph. Any questions? So I'm trying to illustrate the relation between delta and epsilon. So hypothetically speaking, if the epsilon is 0.5, that causes us to, that is our requirement. Okay, so this is the requirement we would want to do, and this is what we have, the action that we have to take to satisfy the requirement. So this part is like the target. I mean, the limit value is a target. Now this is, as you want to get that satisfied, all you have to do is get this satisfied. So this is like action or something that you have to something you have to make sure happening in order to reach that target. All right. So what we're going to do is to find out what action are we supposed to take in order to reach that target. So we want to get the y value between these two. And we draw that band, reach those 2 red points. Now we reach back to the x-axis, get these 2. And remember the 4 is in the middle. Now we want to find how far this is and how far that is. Now after the calculation, this is 1.75 and this is 2.25. Now it's time to choose our delta. We have to find a certain range where this is all satisfied. So as you're choosing your delta, you always choose the small one. So you choose 1.75 as what the delta is supposed to be. That's going to be our delta. So on the left side is a graphic display on how do you choose delta when the epsilon is given. So normally epsilon is any number, pick any number, you can find out what is supposed to be the right delta to use. Now, that is how we do it graphically, but we don't always have the graph, and here is how we do it numerically. So you can start with your target. We want to make root 2 minus 2 absolute value less than 0.5 because epsilon is chosen as 0.5. All right, so with that, we know that 2 plus 0.5, 2 minus 0.5 are the boundary for the root of x. Then we calculate this 2, and we know this 1.5 and 2.5, which is the boundary for the root of x. We square all three. Square 2.5, square root of x, square 1.5. We get x value. All right, but our goal is to find boundary for x minus c. And c is 4. So we need to know what is x minus 4. So we do x minus 4, minus 4, minus 4 on all the boundaries. And then we end up getting a boundary 1.5 and 2.5 at the left and at the right, right? And then once you find these two boundaries, we always choose a smaller one. So 1.5 is the one we choose. Smaller absolute value. And so you use 1.5 as a chosen delta. This is a process to illustrate that whatever the epsilon you're chosen, using this process, you can always find the appropriate delta for it. That's the idea. So the definition for a limit is whatever the epsilon you're choosing, any epsilon, we're able to, this says exists, we're able to find a delta that is, this is satisfied, then this is satisfied. If this is good, and that is the limit definition, right? When does the limit does not exist? The limit does not exist that if for a certain epsilon, we're not able to find that delta to make this happening. So this is not getting satisfied, no matter how you do this, how small the delta is, this is not happening, then we would say the limit does not exist. So the opposite of this is the definition for the limit does not exist. So what was the limit does not exist? Let me just try to compare the two. All right, over here, this is a epsilon delta definition for limit of f of x as x approaches c equal to L. All right, so the logic opposite is the definition, the proof that limit of f of x at x approaches c is not L. So how do we prove this? So if there is one epsilon, exists a epsilon, so that no matter for all the delta, for any delta, okay, and you cannot find for any delta there exists. I mean, you see, any is for all of them. This is one of them. So the logic backward is each other. So the backward from here is here, and then the backward from here is here. So the definition for the limit does not exist is the opposite of when it exists. So there's an x such that even though x minus c is less than delta, but somehow f of x minus L is bigger than epsilon. So that is the logic opposite of that part. Okay, so this is how we prove the limit does not exist using the epsilon delta definition. We don't really talk about this a whole lot, but just want to explain that there's actually a formal definition for it. All right. Okay, over here is really a mathematical exploration. When you are proving the limit, you actually have to go through this. This is a actual proof that the limit does not exist. The limit exists. All right. So in order to prove the limit exists, you start with your target, which is essentially this one. Right? We want this to happen. If you try really hard and this is not happening, then that will be what happened here in the limit does not exist. So you start with there and then try to. It's kind of like starting here and then slowly finding out the boundary for x minus c. You're able to get to the right delta to make this happening. That is happening, and then we're pretty much done with the limit, the proof of the limit. The process itself is very algebraic. So sometimes it's not that easy. We have to find different ways to find the appropriate delta. So you can see. For a student in the proof class, they were always like, what would be the right delta? They'll have a lot of discussion on the choice because you, as the mathematician, as the one solving the problem, you have to answer the question that there exists a delta. Since you see it exists, what is it exactly? What was the formula for it? That is the part that we are struggling. But in our homework question, most of the time we use a graph or use a numerical calculation. Calculating one delta is easy, but calculating all the delta, the formula of the delta is hard. And this is a proof. So you start with say root of x minus 2 less than epsilon. Why is it like so? Root of x, this minus this, root of x minus 2 is less than epsilon and bigger than negative epsilon. And then you add a 2 to all three. Plus 2 here, plus 2, that cancels the 2, plus 2 plus epsilon. So now we get here. Our ultimate goal is from these two distances, we're going to find the distance between x and 4. So number one, you have to find the x, and then you find the x minus 4. So we'll square all three. Square this, square this, square this. Now we know the boundary for x. So start with the boundary for y, and then we're slowly moving on to get to the boundary of x. And then red time. All right, and then we will have the x by itself, and then we'll minus 4. We had that one and that one. Now we have to decide, is this one bigger or is that one bigger? And we have no idea. So you will have to determine whatever is smaller of the two is going to be the right delta. So finally, we have a little formula for delta. Delta is the minimum value is or less. We always pick a smaller delta to make sure the distance is small between the x and the limit point. So it has to be minimum between this number and that number. Okay, so we say as long as the delta is smaller than this quantity, then whenever x is close to c, close to 4 by that delta, then the root of x will also always close to 2 by the epsilon. Any question? So this is a strict mathematical proof for linear calculation. Many of the calculation involve really carefully studied relation. Yes?
What are we finding again?
We're trying to determine the right delta. Yeah. So delta essentially is a boundary for x minus 4. So all these processes trying to get x minus 4 being quantified. Any other question? So we're trying to start with quantifying root of x minus 2. Eventually end up being quantifying x minus 4 because we're trying to, if you want to get y close to L, how do we do that? By making x close to c. If you want y to be close to the value, we can achieve that by making x close to x value. This is the second example on the same process. So this is trying to prove that limit of x squared equal to 4 if x approaches 2. So that's pretty common. I mean, you think about 2 squared equal to 2, and that seems to make sense. But the mathematical proof is actually not so straightforward. So what do we do? It's the same logic. You start with, you want to prove these two are close. When these two are close, you can start with how close these two can be. So let's think about how do we write out the answer, write out the solution without reading. I mean, even if you read the textbook, it seems to be messy without your own interpretation of it. So basically, the idea is for any epsilon positive, for any epsilon positive, if we really want the y value, the x squared and 4 to be close enough. So if we want x squared minus 4 to be less than epsilon, epsilon is very small, so suppose epsilon is 0.01, that means x squared minus 4 is less than 0.01. That is saying x squared is very closer to 4 already. That kind of indicating it's approaching to a value 4. But we're making it hypothetical, so let's make we're making epsilon stay as an arbitrary number instead of pick out a number. I'm going to start looking at how do we rewind the relation here. In the text, we actually go from the forward, but when you're thinking about the solution, you went by a backward relation. We can do this. This is like x squared minus 4 would be less than epsilon bigger than negative epsilon. So x squared would be between 4 plus epsilon and 4 minus epsilon. I repeat what we were doing earlier. And our eventual goal is to get x minus 2 being represented. So here we have a slight problem that is this square. So we have this issue, is this 2 both positive or not? And if one of them is negative, see this one, if epsilon is small enough, we're assuming epsilon, this is positive, is less than 4. If the epsilon is small number, supposedly, so ideally it should be less than 4. So this will be positive, this will also be positive. Among the two positive, we're now able to find the root, right? We eventually need to find x value by itself. So then x will be between root of 4 plus epsilon and bigger than 4 root of 4 minus epsilon. So if we're able to find a boundary for the x value, so I'm going by a logic for the other question. This is a little tricky way that we end up have a factoring process, but the method here involve a lot more algebraic than the previous question. So I went by a different approach here. We'll find the x minus 2 is what we try to write at. And we 4 plus epsilon minus 2. And this is going to be root of 4 plus epsilon minus 2. Okay, and then ultimately we need to know which one is bigger among the two, because we need to know x minus 2 is going to be less than delta. We're going to choose the appropriate delta. So we're going to choose between this number and that number. Normally we choose a smaller x value. So you're going to put in. All right, but we don't know which one is bigger or smaller. So the delta has to be chosen as a smaller one between this x value and that x value. And that's a more direct way of solving this question. All right, I think that approach is okay, but in the text we have we factor this too. After you factor, we realize this is x minus 2, which is what we aim to get. We want to have a boundary for x minus 2. So if we go from here, then divide the x plus 2, x minus 2, that's less than this. So then if we put a boundary for this, that could be our choice for delta. So the rest kind of follow that idea. This is like a shortcut way. As you can see, mathematical proof of a limit involve sometimes more than one approach. So one person might write out their proof this way, and the other person might probably going to go by slightly different ways, since logically is more correct. Any question? All right. Proof is not required in the course, but then it's better if we do understand how limit works. Let's try a few questions from the assignment so we can see. Okay. This is the first question. It's more about the definition. It says that the definition for f of x equal approaching L, limit of fx equal to L when x approaches C. For that is the notation. For that notation, the epsilon delta definition says for all or for any epsilon positive, there exists or there is a delta positive, so that whenever x minus C is less than delta, we would have f of x minus L less than epsilon. So this is the definition. And then here we're going to try to prove what if the limit does not equal to L. So we are going to write out the opposite of the limit exists, which is the limit does not exist. If the limit does not exist, then for all epsilon will be switched to for one of the epsilon. The exists will be switched to for all the delta. So that is kind of what I'm writing here. So 1, 2, 3, 4, 5. So I guess we have a couple of wording for it. So we're gonna the statement. So rigorously, for us to prove the limit of fx is not L when x approaches C, we will say number one is the wording. It starts with there exists, right? There exists epsilon, so there is some epsilon. So I will start with 7. There is some epsilon positives. So for all the delta, right, going forward, there is some epsilon positive for all or for any delta positive. So that's 1, 2, 3, 4, and then you go by this one and that one. The next one will be for all the such that for all the delta, no matter what was the delta, you will be able to make fx close to L. So we would go for the delta, which is number 3. 1, 2, and then 3. For all the delta that satisfy x minus c less than delta boxes. I know the last one is limit is this one 6. And that should say 3. There's 8. I rearrange 1, 2, 3, but 1, 2, 3 is already over there. Okay, for there exists an epsilon. For all, such that for all delta bigger than 0. Okay, this should be the so missing 1, 2, 3. So which one is missing? There's 8, right? Which one?
You repeated 3 right here.
Right, and so who is number 8? Number 8. There is some x such that so it's here or here. In English, so let's try to connect them. So start with there is some epsilon such that for all delta bigger than 0 and I have to put a somewhere. Wise. Try to go. There is epsilon. There is so for all, and that will be number 6 delta. So it's 1, 2, 3, 4. Such that for all x. So instead of for all x, it should be there is some x. So number 8 should be entered here. And that should be it. All right, so that's really the sequence. Sorry about it. So it's try to enter words in this place, so it won't be interrupting with. This is a logic definition for the limited that exists. I'm doing it together with you, so actually, you kind of know the order of any question. But you gotta remember the words because they might switch around those numbers when it's your version of the question. That's the epsilon definition, the definition part of the wording. And all right. So let's try to look over it according to the epsilon delta definition. So we start with the symbolic part, and then we slowly moving on to the definition when there's a few questions which has graphs. I feel like the graph question is here. Okay, so this is one related to the graph, and you draw the band as necessary. So for example, this is still the root function. So we are trying to see here, we're trying to find the appropriate delta. So that's the ultimate goal. And we already have the epsilon. So in the question, the epsilon is chosen as 0.2. So we don't get to decide like arbitrary epsilon. This epsilon is chosen by the system. So we want x to be close to 3 when x close to 9, the root of x close to 3. So we're drawing a 0.2 band around the number 3. So it goes 3 minus 0.2, that's 2.8, is 3 plus 3.2. That red band is indicating a band corresponding to the curve. And then you go down vertically toward the x-axis, you are aligning at these two numbers. Graphically, it looks like this left side has a smaller radius, and the right side has a bigger radius. This radius is what we are going to be using as our delta. Because we're trying to find, this is a 9, this is any x value. The distance between a random x value within the band, the distance between x and 9, is going to be smaller, right? It has to be smaller than this one, because if it's smaller than this one, you might just win a little bit out here if you chose the wrong distance. So we have to pick a smaller radius. So within that radius, the y value will stay within the band. We're trying to provide a boundary for the x value. So stay in here instead of go out of it. We're making it as close as possible to 9. So then the y value will be as close to 3. Any question? We okay? You can calculate this actually on the computer, but since the graph is already here, to me, I can see that's 9. This is 8, right? So between the 9 and 8, what is here? So this is 1. This is 9, that's 10. So this little over 10. So this distance is 1 plus a little. So this is also 1 plus a little. So I'm kind of guessing it must be, the delta must be 1 point something. See 1.1. So I'm using the graph to make educated guess. So let's make it small. Close enough. Don't want to make it too small. All right. Do some calculation. So it's like you back up the graph. Maybe I'll save the time. So let's calculate. Let's do the same calculation that we were already doing earlier. If you feel more comfortable with equation rather than equally, you can also choose to do that. So essentially, we start with this. And we're slowly getting to get here, so we can choose the delta. So that's really the idea. So you're going to start with root of 3 minus 3 is less than 0.2. So resolving this, getting this to boundary, all right? But you can also do it algebraically. It says root of x minus 3 is less than 0.2, but bigger than negative 0.2. Then you want to get it by itself, so plus 3. So root of x is less than, so we're going to plus 3. Yes?
3 plus 2, 1, 0.2?
Yes.
Yeah, you add 3 to both sides.
Right, thank you. So we add 3. Okay, so that way we get the root of x by itself. So this is 3.2. This is going to be 2.8. And that's exactly what's showing in the picture. So far we're on track. And now we're going to get x by itself. So x is less than 3.2 squared, bigger than 2.8 squared. Okay. We have to remember where we're going. We're trying to go for x minus 9. So we have, so we get x already, but we still need to get x by minus 9. So we're gonna minus 9 because we eventually need to put a boundary. Minus 9, minus 9, minus 7. And now we have this. We have x minus 9 is now 3.2 squared minus 9, and then 2.8 squared minus 9. Now it's time for some calculations. So anybody? Okay. A number for this, like this must be 0 point something. Yes.
Where are the 9 coming from?
It's in the limit. It's step 9.
Oh.
So we're trying to make x close to 9. So if x is close to 9, then the x will be close to 3. A number. We have this.
Oh wait, I have the other one.
We have this one. What's this?
Basically, if you square root it and then minus subtract 9, it's 775.
You mean square?
Oh, square root. Oh, oops, my bad.
Square. Yeah.
You got 184.
What?
It's supposed to be small.
I keep forgetting. Sorry, I'm going in autopilot.
It's okay. Yeah.
7.81. Sorry.
Oh, it's an absolute.
7.84. You mean minus that?
Oh, minus 9.
Yeah.
Negative 1.1.
So this is negative 1.6, and this one is 1.24. All right, but remember we take absolute value, so we gotta take the absolute value x minus 9, so you're gonna take absolute value here. So you have to take absolute value of these two, and then after we take absolute value, this will be 1.16, this will be 1.24. For delta, we always choose a smaller one because we're making a guaranteed smaller radius. So, and we end up getting 1.16. So that's our chosen delta. I hope that kind of makes sense. Are you okay?
Yes.
All right, so we've been repeating the process here. If I made anything confusing, please let me know. We'll go through the rest of the example. I'll try to help as much as possible with this assignment. Obviously, I did spend some time on the proofs, but it's not that high on the priority. But having some understanding is helpful, just in case later you do need to prove something and there's some theoretical foundation now. All right, that'll be it for today. Thank you.
At that point.
No, I can see that.
So, and you plug in the 68. 3 times 1. So calculate that. That's one y value. And the second one is t equals 1.01. We again try to calculate it, but it's instead of 1, we do 1.01.
So it's the same thing, you're just plugging in.
Right, it's the same thing. I didn't finish the calculation because I was like trying to save time. So instead of 1, use 1.01. And if you put this into a calculator, you can very well get the number. That was this. So they're pretty close after the subtraction. So if you want to find the slope, you now have 2 y value, 2 x value. So what you're going to do is subtract the y value in the numerator, and then you're going to divide by the subtraction of the x value. And that's really the calculation.
Yes, how long we're calculating the average speed between this point and a point really close to yeah. But you have, in order to find that, you have 2 points. And so remember our first one.
On the top.
That's the same thing.
Okay. This one. Oh, so making it higher on the screen. Yeah, I see. So this one was too low. Yeah. I understand. Yeah, I'll definitely remember it. Okay, tomorrow. Thank you.
So, for the finance, I used,
Yeah. I see you already did some calculation.
yeah, I dropped,
Are they correct? Let's see if you submit it. It will show you whether you are.
oh, not,
Is that an internet issue?
yeah.
Yeah. So do you remember which question was it? Is the first section?
Yeah.
Question 8.
Number 8.
Oh, for me, it's, I'm pretty sure it's question 8. Check number 9.
Oh, yeah.
Oh, yeah.
Okay. So if you do the calculation, you're gonna start saying the slope. They should be very close to each other.
Oh, they should?
Whatever,
And mine was-
whatever- yours are not all different. So
Yeah.
if this is a sequence of number that seems to be closer to each other, you can guess whether they're the limit, where the limit is going to. You might have to double check your calculation to see why are they not approaching
Mhm.
common number.
Yeah, that's why I was confused because they weren't approaching a common number, so I wasn't sure if I like
Uh-huh.
did the second part wrong. and
You
the
might,
first.
this is calculating the slope, so then the P is already given, Q is the one that you have to calculate. So if you're using like the first one, so the point, this is 0.5, this is 1, so 1 minus 0.5 is the 0.5 in the denominator. All right, and the numerator should be subtraction of the y value. This is one, the numerator, the first one is already like 1/2. And then the second one, I was using this one minus this one. So then 1 minus 0.5, 1/2 minus this is going to be 0.5. So then it's going to be minus 1.5 over 1 plus 0.5, which is 1.5. Right, so you can see the first one, if you calculate the slope.
Oh, yeah,
directly. So that one, I think I saw one.
Yeah, I think I got that.
That seems to be reasonable.
Mhm.
And then you can change it for the rest. For example, when it's 0.9, it's closer to 1 now. 1 minus 0.9, the denominator is going to be 0.1. And then the numerator has some similar calculation. I tend to write down the calculation because it's easy to say, what did I do last time? This does not change. This one's going to be 0.9. So we're going to change the 0.5 to a 0.9. And then we can see slowly where the finger is going.
Yeah, I think I got the first like 5 right, and then I just messed up on the later 5. That's
Uh-huh.
what I did.
Right. So try to look at the calculation to say, if everything was right, they were supposed to be close to the same number,
Oh,
leading to the same number.
I'll go to the library and do that.
thank you.